Hello, future engineers and subscribers. In this video, I'm going to present uh, problems and derivations and explanations about the resultant of coplanar force systems. And then I also include loadings here, line loadings, the derivation of the equivalent force, and then the location of that force. And we'll have also sample problems on equivalent force systems, equivalent coplanar force systems. So I hope that through this video, your knowledge, your skills in statics will be enhanced, thereby preparing you to become better engineers in the future. So I'll now discuss the resultant of the general coplanar force system. So let's have here a body that is subjected to these original forces. So let's just limit the number of forces to 3 for simplicity. You can even make that to 2, but let's have these 3 forces, namely P, Q, and S, acting at these specific points in the problem, maybe. So remember from axiom of mechanics, one axiom of mechanics, that we can add any number of equilibrium forces without altering or changing the external effect of the original system. So this is the original system. And if we add, let us say, 2 forces in equilibrium applied at G as shown, then take note that the addition of these equilibrium forces does not affect the external effect of the original system. Then we add another equilibrium forces, let's say Q, acting at G also. So again, the addition of these equilibrium forces Q does not affect the original external effect of the original system. Then finally, we also add set of equilibrium forces, S in this case, acting also at G. So the original system is not affected by the addition of these 3 sets of equilibrium forces. Now notice that this P here and that P there constitute a couple. So we can remove them and replace them with a clockwise couple because the effect of P would be clockwise. So we remove them and replace with a clockwise couple, and I'll call that uh, C sub P, couple due to P. Then notice also that this Q here and that Q constitute a counterclockwise couple, so we can remove them and replace them with a counterclockwise couple C sub Q as shown in the figure. And finally, we also replace S here, these two set of forces, uh, S and S, which constitute another couple, which is counterclockwise. So we remove them and replace with a counterclockwise couple called C sub S, as shown in this figure. Therefore, this original set of system can now be replaced by, you look at the forces, they are now concurrent at G. So these forces, by principle, can be replaced with a single force or by a single force, and we call that the resultant, as well as these couples. So remember that the couples are free vectors, and therefore they can be shifted to any point on the plane, on their planes. So we combine these couples and we will call the resultant couple as C sub R. And since there are two counterclockwise couples, let's assume that the resultant is a counterclockwise couple, and let us also further assume that the resultant of the forces P, Q, and S lies in the first quadrant, that it is pointing up to the right, making an angle with the positive x-axis of theta in general. So this is just the generalization based on principle. So this is now the system. The original system is now replaced with a single force R and a couple which is counterclockwise as shown. So these are by principle, remember you add P, Q, and S vectorially, and that's the resultant force, which is also a vector, but you can compute its horizontal and vertical components by expressing each force here in vector into x and y components, then you add corresponding components. So that's why you have this result here. And that's an easy job in finding that resultant. Rx is simply summation forces of x, and Ry is summation forces of y. So let's focus first on coplanar for systems, 2D systems. Then this is the resultant couple, which is counterclockwise. Then in general, this system, this is the real system, is further reduced to. So notice that R is acting at point G, where G is an arbitrary point. Then we have the couple, resultant couple, which is counterclockwise. The system may also be replaced by a single force R with its perpendicular distance from this arbitrary point G specified as D, as shown here, so that the resultant couple or the moment of R, the moment produced by R is counterclockwise about G, so R should be below G as shown here, but with the same inclination, of course, and the perpendicular distance specified as shown here. That's the perpendicular distance, such that the moment of R about G, R times D, is equal to C sub R, C sub R. So the original coplanar force systems may be replaced by a single force and a couple, a force couple system with a force acting at an arbitrary point G, as shown here in this case. You may also encounter, so this is one condition maybe in the problem that you will be confronted to. So R and C sub R with R at acting at G. Then a force R with its perpendicular distance D from arbitrary point G specified as shown here, such that the product of R and D, which is equal to C sub R also. This is the way you compute or derive this perpendicular distance D. So of course, that's easy to remember. So it follows that the moment of the single force R about this arbitrary point should be equated to the moment, the resultant couple, which is C sub R. Then finally, we can also replace the system with a single force R and with specified intercepts. So take note that if I call this theta, this is also theta, and this is also theta, the angle between the normal line and the vertical angle of inclination. So I already also explained that in the preliminary part of statics. Then a force R with its intercept specified. We have the x-intercept and this is the y-intercept as shown. And remember that you can move the force along its line of action only. You cannot transfer that to any other point except points on its line of action by principle of transmissibility of a force. So if the force and of course its components are placed on the y-axis, on this vertical axis rather through G, then only the x component will have moment about G. Likewise, if this force is moved to this point on the horizontal axis through this arbitrary point G, then only the y component will have moment about G as shown in this figure. So there's no need to name the x component. And take note that the sense of moment of this vertical component is also counterclockwise, just like this. And in this case, if the force is moved on this vertical axis through the arbitrary point, only the x component of the resultant force will have moment about G, and take note the sense is maintained counterclockwise. But remember, this is the general illustration or the dealing with force systems. The resultant couple may not be counterclockwise, it may be clockwise. But in general, let's consider the resultant couple as counterclockwise because that's the positive assumption by right-hand rule or right thumb rule. So this is the x-intercept, which is denoted by A, and this is the y-intercept, which is denoted by B. So from the figure, R times D is also equal to Rx times B, Ry times A, and it is equal to C sub R. So Rd equals Rxb, Rya equals C sub R. Likewise, from the figure, the perpendicular distance is either A sine of theta or in this case B cosine of theta. That's the perpendicular distance, either A sine theta or B cosine theta. You just apply trigonometry. You don't need to memorize that. You have to understand the geometric meaning using trigonometry. I now discuss the resultant of coplanar force systems with line loads. And in this part, I'm going to have the general expression for computing the equivalent force representing the line loads as well as its location, of course, by integration. In general, this may be the line load, which is a function of the distance x if the length is L. So this may be a distributed load in newtons per length. So the area, therefore, under this curve or line load is a force. So let's have a strip and its distance from the origin, let us say from the y-axis is x, and this is the rectangular strip with height w in general at that differential thickness of the base dx. It is constant height, and the force will be acting at the point G in general, and that distance is xg, which I am going to derive also and explain. And the force on this rectangular strip is, of course, the differential force dF. So dF is the area of this rectangular strip, which is thickness times the height of the strip. So integrating F therefore is integral of this W times dx, which is integral of differential area. So therefore, we interpret this total force F as simply the area of this uh, line load. So F is equal to integral from 0 to L of W dx, and I hope that you can interpret that as simply the area under this line load diagram. Then similarly, we apply Varignon's theorem here in locating the point where this F acts, and let's derive xg. So by Varignon's theorem, the moment of the resultant, which is F times xg, is equal to the sum of the moments of its components. One component is df, and sum means elongated s, so we'll have the integral form. Integral of df and the moment arm of f is x. So fxg equals integral from 0 to L of x df. Take note, this is df. And that's the moment of area, the interpretation. So let's expand this by treating the common loadings or common area. Let's say we have this nth degree curve. The equation of this curve is in general y equals kx to the n. This is the given intensity of the load, WR, in Newton or kilonewton per meter. Then this is the differential force. Again, the height is W, and the distance of the centroid of that rectangular strip from the left is denoted by x, and this g here is xg, and we will call this xr because it's easy to remember xr than xg expression as I derived it here. So this is the length of the line load, which is L, and the intensity at the right is WR, and of course here it's 0. That's why we have y equals kx to the n. So at this point here, y is WR and x is L. So therefore, WR equals KL to the n. The equation, the value of W therefore is K, which is WR over L to the n, times x to the n. So F equals integral 0 to L of W, which is K, WR over L to the n, that's the value of K, then x to the n dx. Of course, this is constant, so if we integrate x to the n dx, it's just x to the n plus 1 over n plus 1 from 0 to L. So we put the constant before we integrate it. So we have WR over L to the n, then integral of x to the n dx is x to the n plus 1 over n plus 1 from 0 to L. Simplifying, that's WR over L to the n times quantity L to the n plus 1 over n plus 1 because the lower limit is 0. So take note that L to the n plus 1 can be written as L to the n times L. So we can cancel L to the n, leaving L to the n plus 1 over L to the n as just L. Therefore, the force, which is the area under this line load diagram, is simply the product of WR, intensity of the load, and L divided by n plus 1. So that's it. Then next, we derive xg by Varignon's theorem, or from this principle here. F times xg equals integral of moment arm x differential force w sub r over L to the n, x to the n dx. So the right side can be easily evaluated. That's x to the n plus 1. So the integral of x to the n plus 1 dx is x to the n plus 2 over n plus 2. So f is WRL over n plus 1, then times xt equals WR over L to the n, then x to the n plus 2 over n plus 2 from 0 to L. So we cancel WR and we combine L to the n and L here. After cross multiplication, then we have n plus 1 in the numerator. So xg equals n plus 1 times L to the n plus 2 over n plus 2 times L to the n times L, which is L to the n plus 1. Again, L to the n plus 2 divided by L to the n plus 1 is L. Therefore, xg is n plus 1 over n plus 2 times L. And do not, you can derive this by your own also. But as I said, it's better if we derive a formula for XR because it's easy to remember than this formula here. But also, this is also a very easy to remember formula because we have n plus 1 over n plus 2, then times L. So XR is L minus XG, and XG is n plus 1 over n plus 2 times L. So we have Ln minus 2L, then minus Ln, so Ln will be cancelled, minus L. So 2L minus L is L divided by n plus 2. So XR is simply L over n plus 2. It's easy to remember. Now let's verify these formulas for F as well as for this XR or XG for common cases like a rectangle where n is 0 degree for that case. So F is WR times L, which is just the area of the rectangle, which is base times height. WR height, L the base, right? And if you use this formula, n is 0, so WRL over 0 plus 1 is WR times L. So that's why that's the result. And of course, if you use here uh, 0 plus 1 over 0 plus 2, that's 1 half of L. So that's why XG is L over 2 and XR is also L over 2. Next, for a triangle where n is 1, uh, FR is one, of course, 1 half base times height. That's the interpretation. You don't need to memorize. But in general, you have to familiar with this. You can derive this by your own so that you can easily remember this. So of course, the area of the triangle is 1 half base times height, which is that result. WRL over 1 plus 1 is 1 half of WRL for rectangle, for triangle rather. Then this is 2/3 of L because 1 plus 1 is 2 over 1 plus 2, which is 3. So 2/3 of L. And XR would be L minus 2/3 of L. So that's why it is L over 3, or L over 1 plus 2 is L over 3. And you're supposed to familiar with the location of the centroid of a triangle. Then finally, for second degree curve, we have a parabola here. We call this spandrel of parabola or complementary parabola. So this is 3/4 of L because we have second degree 2 plus 1 is 3 over 2 plus 2. So 3/4 of L xg, and XR would be L minus 3/4 of L, or using this formula here, L over 2 plus 2 is L over 4. And the area is 1/3 base times height for spandrel of parabola, or you use this formula here, WRL over 2 plus 1, so that's why it's 1/3. So I hope that you got it and you can derive it by your own. You're through with integral calculus, so you can easily set up these formulas or derive these formulas. Let's now have an example. So this is the first example on resultant of coplanar for system or equivalent systems. So two systems of forces act on the beam. Are they equivalent? So we have system 1 and system 2. By the way, this problem is taken from the book by Bedford. So in this system 1, let's assume that downward is positive. So Ry is 100 minus 50, and it is 50 newtons downward. So remember that the assumption here is downward as positive, but anyway, let's specify it. So R is 50 newtons downward. For the resultant couple or moment, then we have to consider here, let's call this the origin or the left end. So the moment is clockwise and it is 100 times 1 as shown. So MO is 100 times 1, so it is 100 Newton meter clockwise. So remember that the sign convention is positive counterclockwise. But in this case, anyway, it is labeled and the sense is specified that it is clockwise, 100 Newton meter. In system 2, there's only one force and it is going down. So the resultant, of course, is 50 newtons downward also. But both the resultant as well as the resultant couple should be equal so that we can say that both systems are equivalent. So for the moment about the origin, it is also clockwise, 50 times 2, and 50 times 2 is 100 Newton meter clockwise. So we conclude that systems 1 and 2 are equivalent. That's the explanation for this problem. So for this second problem, two systems of forces and moments act on the beam. Are they equivalent? So we have here the first system and the second system. For the first system, let's again assume that downward as positive because by looking at it, it's obviously downward force is greater in magnitude than the upward force. So 20 minus 10. So for system 1, the resultant is 10 pounds downward, as indicated here. Then for the moment about O, let's again assume that clockwise is positive. So it is 20 times 4 minus this counterclockwise moment, which is 50. You can make the sign convention counterclockwise uh, positive and upward force positive if you want. You can also do that as long as you consistently follow that sign convention. So in this case, MO is equal to 30 pound-foot and it is clockwise. The sense is clockwise. For system 2, R is also 20 going down minus 10 going up. So it is 10 pounds downward. So with regards to, so R 20 minus 10, so it is 10 pounds downward. With regards to the moment, we have 30, which is clockwise, then minus 10 times 2 counterclockwise. So that's why the resultant couple or moment about the origin O is 10 pound-foot clockwise, same as that clockwise, but the magnitude is different. Therefore, systems 1 and 2 are not equivalent. So that's the conclusion. For the systems to be equivalent, both the resultant as well as the resultant moment or couple must be equal. Problem 3. Three forces and a couple are applied to a beam, which is system 1. A, if you represent system 1 by a force applied at A and a couple, what are F and M? So this is system 2. We represent this system 1 by an equivalent force couple system, and this is now the system 2. Now, in this problem, F is written boldface, so that means it must be in vector form, and M is not. Therefore, M is just magnitude with the sense, of course. So, with the sense, although we are asked to compute for M, and that's the anticipated sense because that's the positive sense which is counterclockwise supposedly. So for system 1, again, we consider downward as positive. R is equal to 20 plus 30, then minus 40. So R is equal to 10 pounds downward. Then for The moment about A, again, we consider clockwise as positive. So 30 times 4, which is clockwise, then minus 30, which is counterclockwise, minus the moment of the 40-pound force, which is also counterclockwise, 40 times 2. So MO or MA is equal to 30 times 4 minus 30, then minus 40 times 2. So it is 10-pound foot and it is clockwise. That's for system 1. The resultant is 10 pounds downward and the moment about point A is 10-pound foot clockwise. So therefore, for system 2, F will have a magnitude of 10 pounds downward and M is 10-pound foot clockwise. Or since we are obliged to this present our answer F in vector form, so it is equal to negative 10 J pounds, and the moment is negative 10 pound foot because it is clockwise and counterclockwise is positive. For system 3, F is again 10 pounds downward or 10 negative 10 J pounds in vector form, but let's choose this scalar value, which is downward. Anyway, the direction is labeled or indicated. So the moment, therefore, is 10 downwards times d. That's clockwise. Then we equate that to this clockwise moment of 10-pound-foot. So Fd equals 10-pound-foot clockwise positive. So F is 10 pounds downward. So that's why its moment about A is clockwise times D equals 10. So D is 1 foot. So that's for this problem. Problem 4, again, this problem is taken from the book by Bedford. So three forces act on the beam. A, represent the system by a force acting at the origin O and a couple M. So F should be expressed as a vector because it is written boldface here. The couple will just be magnitude and sense. Represent the system by a single force. Where does the line of action of the force intersect the x-axis? So that's the second question. First, let's look at the given force system. Rx, of course, is 30 newtons rightward, or Fx is 30 newtons rightward. Then Fy is 30 plus 50, so that is 80 newtons upward. So we write F in vector form as quantity 30I plus 80J close newtons. So that's the force and the moment. So this time counterclockwise positive. So MO is equal to, or M is equal to 50 times 10, then minus 30 times 5. So MO equals 350 Newton meter. So that's also the couple M acting at the origin and 350 Newton meter counterclockwise. So to answer letter B, the force F is also the same, 30I plus 80J. And for the line of action, intersection of its line of action on the x-axis, so reckoned or distance from the origin. So let's have the components of the force on the x-axis. So let us say this is A. These are the components. So only the 80-pound force, the Y component, will have moment about O, and the sense is also counterclockwise. So by principle, 80 times A is equated to 350. So Fy times A is MO. So 80 times A equals 350. A therefore is 4.375 meters. So that's it for this problem. Problem 5, the vector sum of the forces acting on the beam is 0 and the sum of the moments about the left end of the beam is 0. So that means the system is in equilibrium. So determine the forces AX and AY and the couple MA. So summation forces X is 0, so that means the resultant X component of the resultant is 0. So AX plus nothing equals 0, so that means AX is 0. Then likewise, RY is 0. So from the figure, AY plus 200 minus 600 equals 0. And AY therefore is equal to 600 minus 200. So 400 newtons upward. That's AY. Then for MA, we sum up moments about A and equate it to 0 because the vector sum or the sum of moments about the left end is also 0, counterclockwise positive. So MO is summation of moments about origin equals 0, and that is MA plus 200 times quantity 0.38 plus 0.18, then minus this couple 30, then minus 600 times 0.38. So MA equals 146 Newton meter counterclockwise. Then for part B, sum of moments about the right end. So summation moment about the right end counterclockwise positive. So we have MA, which is 146, then uh, plus 600 times 0.18. This is counterclockwise positive. Then minus AY times 0.38 plus 0.18, then minus 30 Newton meter. So MR is of course 0 because the resultant is 0 and the resultant couple is also 0. So this is the other explanation and that's the expected result. Then for part C, if we represent the forces 600, 200, and this 30 Newton meter coupled by a force acting at the left end of the beam and a couple M, so find F in vector form and M. So that is MO equals MB equals mg equals mr equals 0 as the result of this. So any point on the beam you choose, the sum of moments is also 0 because the resultant is 0. Then for part C, R would be equal to F and it is 600 minus 200, this time downward as positive. So F is 400 newtons downward. That's the force, and in vector form, that's negative 400 J newtons. Then for the moment at the origin, we calculate it counterclockwise positive. So this is the answer in vector form. So M, which is assumed to be counterclockwise positive, plus 200 times 0.56, 0.38 and 0.18 is 0.56, then minus 600 times 0.38, then minus 30, then M is equal to 146 Newton meter counterclockwise. So that's it for this problem. Problem 6. If you represent the three forces and the couple by an equivalent system consisting of a force F acting at A and a couple M, these are vectors, what are the magnitudes of F and M? So we're looking for the magnitude only. So this time, let's have the sign convention, which is rightward positive and upward positive. So obviously, there's no other horizontal force, so Rx, which is Fx in this case, I'll just represent it with R, then R is equal to F, is 200 pounds, so Rx equals 200 pounds rightward. Then Ry is 300 minus 200, so it is equal to 100 pounds upward. So therefore, in vector form, R is quantity 200I plus 100J pound. And the magnitude, which is R or equal to F. So the magnitude is square root of 200 square plus 100 square. So the magnitude of F or R is 223.6 pounds. For the moment, we consider counterclockwise positive. So 200 times 5, that's counterclockwise. This 200 pound here has no moment about A because its line of action passes through A. Then 300 times 6 is clockwise, so that's negative. Then 800 is also clockwise, so that's negative. So from the figure, moment about A is 200 times 5 minus 800, then minus 300 times 6. So M is equal to negative 1,600 pound-foot. So the magnitude, because that is clockwise, of course, the magnitude of M is 1,600 pound-foot. And the actual sense is clockwise. So that's it for this problem. Problem 7. This is taken from the book by Hibbeler. Replace the force system acting on the post by a resultant force and a couple moment at point A. So let's consider the forces one by one. Let's consider 250, then this force and that force. So Rx is equal to positive 250 times 4 over 5, then minus 300, then minus 500 cosine of 30. The x component of 500 there is going to the left, so that's why it's minus. So Rx is equal to negative 533.0 newtons. Ry is the y component of 250 is going down, so negative 250 times 3 fifths. Then this is positive 500 sine of 30 degrees, 0 y component for this 300 Newton force. So R sub y is equal to 100 newtons. Therefore, I report the answer in vector form. It is quantity negative 533.0 I plus 100 J newtons. So that's RA. For the moment about A, so let's consider the sign convention counterclockwise. Positive, the x component of 250 is clockwise, so that's negative. So negative 250 times 4 over 5 times moment arm 3. Then the vertical component going down produces clockwise moment about A also. So it's negative 250 times 3 over 5, and the moment arm is 0.5. So plus negative 250 times 3 over 5 times 0.5. Then for this 300 Newton force, it is counterclockwise, so plus 300 times 1. For the horizontal component of 500, it is counterclockwise about A, so it's positive. So plus 500 cosine 30 times 2 meters. And for the vertical component, it is clockwise, so minus 500 sine of 30 times zero point 0.2. So minus 500 sine 30 degrees times zero point 0.2. So simplifying, MA is equal to 441.0 Newton meter, and it is counterclockwise. So that's it for this problem. So problem 8, replace the force system acting on the frame by an equivalent resultant force and specify where the resultant's line of action intersects member AB measured from point A. Then in part 8B, same resultant and specify where the resultant's line of action intersects member BC measured from point B. So take note that we can move the resultant force along its line of action, and we cannot do that for the couple. So for part A, Rx is 25 plus 35 sine of 35. So Rx is equal to 42.5 pounds rightward. Ry is negative 20 and negative 35 cosine of 30 degrees. So R sub y is negative, it's downward, and it is equal to negative 50.31 pounds. Therefore, the resultant is in vector form 42.5I minus 50.31 J pounds. So that's the resultant force for the moment about A. Of course, counterclockwise positive. So we have 25 times 3. Let's have the components of the resultant, and we call the distance of the intersection with the horizontal AB with the intersection with the resultant, and we'll call that A. So moment at A, considering the original force system or components, is equated to moment about A considering the resultant. So it is obviously clockwise. So we have moment at about A is equal to 25 times 3, then minus 35 cosine 30 degrees times 2, which is that, then minus 20 times 6, which is this. So MA is negative 105.62 pound-foot. Considering the resultant components, only the vertical has moment and it is clockwise. So MA is negative 50.31 times A, and it is equal to negative 105.62. So solving for A is equal to uh, 2.0999 feet. Then for moment about B, it is equal to 25. So this is the resultant when moved along its line of action, and this time on portion BC. So the only component of the force that has moment about B is this horizontal component. So MB equals 25 times 3 plus vertical component of 35 is 35 cosine 30 times 4. This is that. So computing MB equals 196.24 pound-foot. Then we equate this to the moment to solve for the distance B. So R is the same, but the moment changes. So we have negative positive 196.24. That's the moment about B. And it is equated to the moment about B due to these components, 42.5 times B. So B is equal to 4.617 feet. Another way of computing B is we have this triangle and the angle that the resultant makes with the horizontal, called that theta. We can solve that tangent of theta is vertical 50.31 divided by horizontal 42.5. And this is also equal to B over this distance, which is, if we denote this by, if this is 4 feet, then because we already solved for the value of A, so that means this is 6 minus A. So equals B as to 6 minus A, which is 2.099. Solving for B, B is 4.618 feet. Problem 9. The three parallel bolting forces act on the circular plate. If the force at A here is has a magnitude of 200 pounds, determine the magnitudes of FB and F sub C, so that the resultant force FR of the system has a line of action that coincides with the y-axis. So that means R is along the y-axis and it passes through the center as shown. So meaning summation of moment about x-axis equals 0 because the resultant acts on the x-axis. In fact, it acts on the also on the z-axis. So we have FC times 1.5 equals or minus FB times this distance is 1.5 sine 30. So minus FB times 1.5 sine 30 degrees. Then minus FA, which is equal to 200 pounds. So FA times 1.5 sine of 45 equals 0. So substituting the value of FA and simplifying, we have FC minus zero point 0.5 of FB minus 200 sine 45 degrees equals 0. So this is the simplification of this equation here, and we cancel out 1.5, so that's why we have FC minus FB times sine 30, which is zero point 0.5 of FB, then minus FA 200 times sine 45, 1.5 is cancelled. Then summation moment about the z-axis equals 0. So we have FB times horizontal distance 1.5 cosine 30. So this is the simplification of the above equations. Then summation moment about z equals 0, FB times 1.5 cosine 30 equals FA times 1.5 cosine 45. So since FA is known, substitute 200 times sine cosine of 45 degrees minus FB times cosine 30 degrees equals 0 after we divide everything by 1.5 from this equation. So we can now solve for FB. FB is equal to 163.3 pounds. We substitute it into equation 1. FC minus zero point 0.5 of FB, which is 163.3, equals 141.42. Solving for FC rather is 223.1 pounds. So that's it for this video. Problem 10. Determine which of the four systems in B through F are equivalent to the force couple system in part A. So this time, this problem is taken from P-TEL and Q-SALAS. So in part A, the resultant force is, it's better to resolve this into or to represent the force in vector form. So it is 10 times quantity 4 over 5 because this is 5 I, then plus 3 over 5 j, and the magnitude is 10. So simplifying, that's 8I plus 6j pounds. For the moment, it's already there. It's 50 pound foot resultant couple clockwise. So 50 pound foot clockwise, that's the resultant. Then each of these forces from B through F should have the same force and resultant for them to be equivalent. So in part B, Rx is 8, Ry is 10 minus 4, so 6. So it is also 8I plus 6J, R. Then for the resultant couple here, only the 10-pound force has moment about this top right corner. So it is 10 times 5 clockwise, and it is equal to 50 pound-foot. Since part B has the same resultant and couple, then it is equivalent to part A, so we conclude B equals A. Then for part C, we have R is 10, same inclination, so in vector form, that's 8I plus 6J. But its moment about this corner here consists of, if we resolve F into its components and put it here, only the y component has moment, which is 6, and that distance is 1 foot. So 6 times 1, then we add this moment due to the original resultant of 50. So it is Ry, which is equal to 6 pounds, then times moment arm 1, then plus 50 equals 56 pound-foot. So R is 8I plus 6J. I already explained that. Same inclination, same horizontal and vertical components. Now, how about the moment about B? It is equal to Ry, which is equal to, there are two components here, Ry, which is 6, Rx 8 passes through that corner. So it is not involved in moment equation. So moment about this is equal to, we have 50 pound-foot plus the clockwise moment of the vertical component, 8 times 1. So 8, sorry, 6 times 1, the vertical component is 6. So 6 plus 50, 56 pound-foot clockwise. So that's the force system in part C. So it is not equal to A because of this resultant couple of 56 pound-foot as compared to 50 pound-foot. They are different. Then part D, which is this, moment there is 10 times 5, 50 clockwise, plus 24, 74, minus the moment of this force, 8 times 3, 24, is back to 50 pound-foot. So R is the same, 8I plus 6J pounds, same inclination. And the resultant couple is, we have 10 times 5 counterclockwise plus 8 times 3 counterclockwise. Then minus supposedly 24. Or C sub R is equal to 10 times 5. Moment there is 10 times 5. That's clockwise. Then plus 24. Then minus 8 times 3. Cancel 24. So it is 50. And it is clockwise. So clockwise positive in this assumption, in this problem. So that's why force system in D is equal to that of A. Then F, this is F. The resultant is 8I plus 6J. So it's the same, but the moment here is 36 minus 80, then minus 6 times 5. So R is the same, 8I plus 6J pounds. Moment about this corner is equal to 6 times 5. Is this clockwise positive? 6 times 5 plus 80 pound-foot, then minus 50, minus 36 rather, then minus 8 times 3. So simplifying, the resultant couple is 50 pound-foot clockwise, so it is equivalent to force system in A. Then F, which is this, R is vector 8I, quantity 8I plus 5J pounds. So the fact that the force the force is originally is, we have 8I plus 6J. This time we have 8I plus 5, only 5J. So by condition of resultant force, it does not satisfy. But let's just continue for a moment also. So R is 8i plus 5j. Then for the moment about that corner there, we have C sub R 5 times 5, 25 pound-foot. So both the resultant as well as the resultant couple are not equal to that of the force couple system at A. So that means F is not equal to A. Problem 11, the force system acting on the machine part is equivalent to the single force R equal to 80I plus 20J pounds acting at the origin O. Determine the force P and the distance B. So P and the distance B. So we have X component. I told that Px. The Y component has no moment about O. So just Px and it is clockwise. So this is equivalent to the system with the force acting at O as shown with these values. So that means moment about O is 0 because the resultant acts at O. So Rx is 80 as mentioned here, and it is equal to the x component of P, which is Px minus 200, then plus 120 cosine 30. Simplifying, Px is equal to 176.1 pounds. Then for Py, let's have that by summing up moments about O. Although Ry is given 20 pounds, we equate that to the Y component of P, then plus 80, then plus the Y component of 120 pounds, 120 sine of 30 degrees. So Ry, or sorry, Py is equal to negative 120 pounds. Determine the force P and the distance h. So P in vector, because this is bold-face, it is equal to quantity 176.1 I plus or minus 120 J pounds. So P 176.1 I minus 120 J pounds. Then for the distance B, we sum up moments about O equate to 0. So MO equals 0, counterclockwise positive. So we begin with the uh, moment summation. So 80 times 3, then minus Px times quantity B plus 6. So plus 200 times 6, then minus x component of B, which is Px, moment arm B plus 6. So this is Px. The x component produces clockwise moment about O, so that's why it's minus. Moment arm B plus 6. And the vertical component passes through O. So that means we have to solve for B from this equation. So 383.4 equals 176.1 B. Solving for B, it is 2.177 inches. So that's it. That's the solution to this problem. Problem 12, replace the coplanar force system that acts on the casting with an equivalent force couple system with a force acting at A point O and in B point A. So for the resultant force first, Rx is 260. So by the way, if the angle measure of the angle here is theta, that's also theta. That's also theta there. So Rx equals 260 minus 200 sine of theta, and sine theta is 3/5. So we have 3, 4, so the hypotenuse should be 5. Then minus 120 times cosine of theta, which is that, and simplifying and substitute sine theta 3/5, cosine theta 4/5. So Rx is 260 minus 200 times 3/5 minus 120 times 4/5. So Rx equals 44 pounds. Ry, on the other hand, is equal to 200 cosine of theta minus 120 sine theta. So Ry is 200 times cosine theta minus 1.20 sine of theta. Cosine theta 4/5, sine theta 3/5. Substitute. So Ry is 200 times cosine theta 4/5 minus 120 sine theta 3/5. So Ry is equal to 88 pounds. So the resultant therefore is quantity 44I plus 88J pounds. So MO equals 600, which is this counterclockwise, then plus 200 times half of the hypotenuse, 2.5. Then no more because this is just a force. So MO equals 1,100 pound-foot. Then for RO, that's the force, 44I plus 88J. You can also move that there, and let's specify C sub RO. C sub RO is 1,100 pound-foot, and it is counterclockwise. That's the resultant couple, which is MO here. So this system is equivalent to the force is applied at the lower end. So there. Then this time we're looking for the new force couple system with the force acting at B. So it is the same force, but what's the moment? So this is counterclockwise. Moment due to 44 is also counterclockwise. So let them plus, then minus 88 times distance. That horizontal distance is 4. So MA equals 1,100, then plus 44 times 3, then minus clockwise 80 times 4. So MA equals 880 pound-foot. So the answer for force couple system at A, the force is in vector form 144I plus 88J. That's RA also. Pounds. Then the couple would be, we just transfer the couple from here to there. So there is already a couple. Sine theta is 3/5, cosine theta is 4/5. Problem 13, replace the distributed loading with an equivalent resultant force and specify its location on the beam measured from point A. So just the loading, let's locate the resultant. These are identical loadings. So these are the values for this equivalent loading here. This is 1/2 of L over 2 times WO. 1/2 of L over 2 times WO is WO L over 4. Same is true here. This distance is 1/3 of L over 2. That's why we have L over 6, which is also equal to this. So the moment of the resultant, R times, let us say, XG, where R is the sum of these two equivalent loadings, WO L over 4 times 2. So R is WOL over 2. Then we apply downward. We apply Varigdon's theorem. R times xg equals WOL over 4 times L over 6 plus WOL over 4 times quantity L over 6 plus L over 2. So WOL over 2 times x sub A, we call that x sub A, equals WOL over 4 times L over 6 plus WOL over 4 times that distance is L over 2 plus L over 6. And that is moment arm is, you just simplify that. So we can cancel WOL and express XA in terms of L. So WOL over 2 XA equals, so let's combine that. That's 5 over 24 WOL square. Cancel WOL and cross multiply. XA is 5 times 2 over 24. So that's 5 over 12 double L. Sorry. 5 over 12 L. That's XA. Problem 14. Replace the distributed loading with an equivalent resultant force and specify its location on the beam measured from point A. So we have here this loading that varies. Then we have, for this trapezoidal portion, I have to divide it into two triangles. So the forces are labeled and indicated as shown in the figure. So we have here for this triangle, I'll call the area equal to F1 equivalent force. Since this is a triangle, the distance of its line of action from this vertical line through A is 1/3 of 3, so that's why we have 1 meter here. For this triangle here, this distance of F2 is 1/3 of 3 meters also, because we have 3 meters here. So that's why it's 1 meter. For this F3 here, say for this lower right triangle, the distance of its line of action from A is 2/3 of 3 meters. So that's why we have 2 meters here. And finally, for this last triangle, the distance 1/3 of 3 meters again is 1 meter from B, then plus 3 meters. So the distance of its line of action from point A, vertical line to point A, is 4 meters. So for the resultant, it will be somewhere here, this portion, and we will call the distance of R from point A, the reference, as XA. So because we anticipate that the resultant lies here and all forces are downward, we consider the moment of R, which is clockwise about A, as positive. So counterclockwise to be negative. You may also consider counterclockwise positive and clockwise negative. It's the same. The result will be the same. So for easy setting up of moment equation in just a moment, then we should consider clockwise positive, because that's the sense of moment anticipated for this resultant. Now, F1 is area of triangle. It is 1/2 of 3 times 15. F2 also is 1/2 of 3 meters times 15. So F1 equals F2, 1/2 of 3 meters horizontal height, 15 kilonewton per meter, so 22.5 kilonewtons. And that is also equal to F2, because it is this 3 meters here and 15 kilonewton per meter, and 3 meters are perpendicular to each other. Remember, area is 1/2 the product of perpendicular dimensions of a triangle. So it's equal to F2. F3 is 1/2 of 3 meters times 10 kilonewton per meter, which is the same as F4, which is 1/2 of 3 meters times 10. So F3 and F4 are expected equal. So it is 1/2 of 3 times 10, so it is 15 kilonewtons, which is equal to F4. Therefore, we can solve now for R, and it is equal to 2 times 22.5 plus 2 times 15, and the direction is obviously downward. So it is equal to 75 kilonewtons. Applying Varignon's theorem, the moment of the resultant is equal to the sum of the moments of its components. So R 75 times XA, clockwise positive, equals, because the moment of F1 about A is counterclockwise, so it is equal to negative 15 times 1. So 75 times XA equals negative 15 times 1 plus F2, which is 15 times positive 1. Sorry, F1 is 22.5 times negative 1, F1, F2, plus F2 times, which is 22.5 times 1, it is positive because the sense is clockwise, and that's uh, our sign convention, positive clockwise in this problem, plus F3, which is 15 times moment arm 2 meters, then plus F4, 15 moment arm 4. So plus 15 times 2 plus 15 times 4. We can now compute XA, and XA is equal to 1.2 meters. So the answer, the resultant is 75 kilonewtons downward, and its line of action is located 1.2 meters to the right of support A. Problem 15. Determine the intensities W1 and W sub 2 of the distributed loading acting on the bottom of the slab so that this loading has an equivalent resultant force that is equal but opposite to the resultant of the distributed loading acting on the top of the plate. So the idea is, because the downward loading is equal to the upward loading, they are balanced. Therefore, this problem is an equilibrium problem. So for equilibrium problem, both the vertical forces downward and upward forces must be equal. And second, the moment of the forces, equivalent forces uh, above this foundation or this plate or slab is equal to the moment of the reaction uh, pressure equivalent to this pressure upward, represented by these intensities W1 and W2 about any point. So in this case, I will select point A as the reference for moment sums calculation, and for you, I leave you select point B as your reference. In fact, you can select any point on the plate. So I'll present A as the reference for moment calculations. I want you to solve the same problem and choose B as your reference for moment calculations. Then, if you can extend, you choose any point on the beam. So let us say you select 4 feet from the left and call that point C. You sum up moments there and make sure that the answers will be the same. So I'll denote the forces above the plate or slab as shown. And so we have F1, F2, F3, and for this reaction, W1 and W2, this is trapezoidal, so I'll divide this into two triangles as shown, and we have R1 and R2. So R F1 is simply 1/2 of 3 feet times 300 pounds per foot. By the way, the distance of these forces can be analyzed as I proceed. I will not level it here, but I will explain it as we move on. So we have this uh, R1 located 3.5 feet from A, and 3.5 feet, because this is triangular, is one third of this total dimension, which is 3 plus 6 plus 1.5, which is 10.5 feet. One third of 10.5 is 3.5 feet. R2 is also from the right, one third of 10.5. So this is 3.5 feet. Therefore, from the left, because I select A as the reference for moment calculation, this should be two-thirds of 10.5 feet, and that is 7 feet as indicated here. So F1 is equal to 1/2 of 3 times 300, and it is 450 pounds. And this is one third of 3, so 1 foot from A. That's two-thirds of 3, so 2 feet from A. F2, which is this rectangular line load, and it is equal to 6 feet times 300 pounds per foot, and that is 1,800 pounds. Then finally, F3, another triangular loading, 1/2 of 1.5 times 300, and that is equal to 225 pounds. Then R1 in terms of W1, 1/2 of 10.5 times W1, and that is equal to 5.25 W1 pounds. R2 is 1/2 of base, 1/2 of this length, 10.5, then the perpendicular height W2, and that is also equal to 5.25 W2. So summation forces vertical must be zero, or downward forces should balance upward forces. That is R1 plus R2 equals F1 plus F2 plus F3. So substituting 5.25 W1 plus 5.25 W2 equals 450 plus 1,800 plus 225. Simplifying, 5.25 W1 plus 5.25 W2 equals 2,475. Let's call that equation 1. Then for the second static equation, that is moment equation, as I said, I select A as the reference moment center. After this problem, if you have time, I want you to select point B, and if you want to extend it further, just to master the principles, you can choose invent another point here. So let's say point C, 4 feet to the right of point A. You can select that as the moment center if you want. Or you select uh, this point or this point through the line of action of R2, so that R2 won't be involved, and you can have uh, you can express you can solve R1 or W1 directly if you select a point here where R2 in terms of W2 passes through, so that R2 won't be involved when you can solve for R1. I'm not doing it here, but I can suggest you select a point here, line of action of R2, so that R2 won't be involved in moment equation. So let's proceed. I select A as the reference moment center, and R1 times 3.5 plus, that's counterclockwise, plus R2 times 7, then equals clockwise moments. So F1 times 2, F1 times 2, I hope you can analyze, it's 2 feet. F2, the distance of F2 from A is half of 6, 3 feet, plus 3 feet, so 6 feet. So plus F2 times 6, then plus F3, distance of F3 from point A is 3 plus 6, that's 9, plus 1/3 of 1.5, 0.5, so 9.5, plus F3 times 9.5. Substituting the values of R1, R2, and F1, F2, F3, so 5.25 times 3.5, plus 5.25 W2 times 7 equals 450 times 2 plus 1,800 times 6 plus 225 times 9.5. Simplifying the left and the right, we have 18.375 W1 plus 36.75 W2 equals 13,837.5, equation 2. Solving equations 1 and 2 simultaneously, we can now solve W1 equals 189.8 pounds per foot, while W2 is 281.6 pounds per foot. So again, my suggestion for easy calculation, you select this point through the line of action of R2 and anticipate that the answer is the same. For further mastery of this problem, you select as suggested 4 feet from A, select that as another point as moment center, then solve the problem again. Problem 16, the bricks on top of the beam and the supports at the bottom create the distributed loading shown in the second figure. So this is the original problem, and when this problem is modeled into this diagram, line diagram, this is the equivalent. So the reactions are also, because we have contact areas here, in a form of line load or pressure in short. So this is the pressure diagram. So the analysis is, because this is balanced, this is a problem on equilibrium. That is, downward force, which is represented by this triangular loading, should be equal to this upward force. And for the second static equation, I select point A as the reference. We sum up moments about A. So counterclockwise moments should be equal to clockwise moments to balance. Now, for the selection of the moment center, you can select, the principle is you can select any point, convenient point, if you want. Then my suggestion again is, because this intensity of pressure is an unknown, and this is also an unknown D, I suggest that you consider a point where the line of action of this reaction passes through, so that that reaction would be involved. And you can have a simpler equation. But in this case, I choose A as the reference. So for the FBD, we have F going down, represented by this triangular loading, and R1 here and R2 here. These are rectangular line loads, so the line of action would be through the centroid of these rectangular line loads. So we have R1 and R2. R1 will be 0.25 from the left, because this is 0.5, and R2 is half of D from the right. So F is 1/2 of 3 meters by 300 Newton per meter, 200 Newtons per meter. So it is 300 Newtons. R1 is area of this rectangular line load, 0.5 meter times 75. And R1 equals, or 75 times 0.5, 37.5 Newtons. R sub 2 is W times D. So that's R sub 2. Then we now have the equilibrium equation, static equation. First, upward forces should be equal to downward force, summation forces vertical, or y equals 0. So R1 plus R2 equals F. R1 is 37.5, R2 is WD, and equals F, which is 200 newtons. Call this WD equals equation 1, and it is equal to 262.5. Call that equation 1. Then moment summation about A0, so counterclockwise moment positive, R1 37.5 times 0.25 plus R2, which is WD R2, then its distance from A is 3 meters minus zero point 0.5 d. So WD times quantity 3 minus zero point 0.5 d equals F, which is 300 newtons. Then moment arm, 2/3 of 3 meters, so 2 meters. That's 2 meters from A. Then let's simplify. Uh, 37.5 times 0.25, then plus WD. WD is 262.5. We substitute 262.5. Then quantity times 3 minus zero point 0.5 d, then this is 600 at the right side. Combining the constants and simplifying, we have this is 9.375, then 262.5 times quantity 3 minus zero point 0.5 d equals 600. So combining like terms, we have 196.875, that's the constant, then 262.5 times negative zero point 0.5 d, negative 131.25d, then because we combined the constants and the right side would now be 0. We can now solve for d. 196.875 divided by 132.25. So d is equal to 1.5 meters. Then we substitute this into equation 1 to solve for w. So w can now be solved and it is equal to 175 newtons per meter. Problem 17. To test the strength of a 625 by 500 millimeter suitcase, forces are applied as shown. If P is, this is P, 138 newtons. So part A, determine the resultant of the applied forces. So the resultant may be expressed as a magnitude, and you have to specify its angle from the horizontal or from the vertical as long as it is clear. But in this case, I'll present it as a vector. I use the components of that resultant to locate its line of action with its intersection with the suitcase. So top and maybe this edge here, and I select B as the reference. You can select A as the reference if you want, as long as it is clearly specified in this problem. So we can compute this angle of this 212 Newton force so that you can easily resolve it into its components. So this angle is inverse tangent of 280, 280 divided by 450, and that is 31.891 degrees. So Rx is 100 plus the horizontal component of 212, which is 212 cosine of 31.891, then minus 180. So Rx is 100 minus 180, then plus x component of 212, 212 cosine of 31.891. So Rx is equal to 100 newtons. Ry is y component of 212 is negative, negative 212 sine of 31.891 degrees, then minus p, which is 138. So Ry is negative 212 sine of 31.891 degrees, then minus 138. So Ry is negative 250 newtons. Therefore, we can now state the resultant in, for me it's in vector form. R is quantity 100I minus 250J newtons. So the answer can be represented by that, or you may compute the magnitude of R, then specify its line of action. That's the other way. So I'll now put uh, this reaction components on the top portion of the suitcase and on this corner here as shown in this figure, and the distance is from B is A. This is the line of action, and you can compute for this angle that this line of action, which is represented by this green colored line, as inverse tangent of 250 over 100 if you want. If you specify the resultant as magnitude and direction, but I just present it by its components in vector form. This is also the other point on the line of action of the force, so that's it. Then the moment about B, obviously, if this is the line of action of the resultant down to the right is counterclockwise about B. So of course, moment summation about B should also be counterclockwise positive. So I use the components first, then to solve for the distances A and B as shown, then I'll use the resultant to find A and B. So moment about B is counterclockwise positive because it is obviously counterclockwise. 100 times 100. For this 212 Newton force here, the horizontal passes through B, so it has no moment. The vertical has moment, 212 sine of 31.891 degrees, and its moment arm from B is 430 plus 80, so that's 450 plus 80, so that would be 530 mm, also counterclockwise. Then plus P 138 times 80, that's counterclockwise. And the only negative moment, because it is clockwise, is due to this 180 Newton force, which is negative 180 times 280. So summation moment about B, or moment about B, is 100 times 100. So by the way, this is the angle that the line of action of the resultant makes with the horizontal if you want to specify it the other way. But this is the better way. I use the components. So MB is 100 times 100. Vertical component of 212 is 212 times sine 81.891 degrees times 530 mm, where 530 is 450 plus 80. Then plus moment of this P here, which is counterclockwise about B, is 138 times 80. Then lastly, minus 180 times 280. That's clockwise. So calculating moment about B is equal to positive 30,000 Newton mm. Then by principle, Varignon's theorem, if the force is here, 100 Newton passes through B, so it has no moment. 250 times A, that's counterclockwise. Then if the force is moved here, the 250 Newton force has no moment, only the 100 Newton force has moment. And its moment is 100 times B, and it is also counterclockwise. So we equate that to moment about B, which is 30,000 Newton mm. So that is 250 times A equals 100 times B equals moment 30,000. So from here, we can now solve for A. A is 120 mm and B is 300 mm. Problem 18. Pulleys A and B are mounted on bracket CDEF. So we have bracket CDEF. The tension on each side of the two belts is as shown. Replace the four forces with a single equivalent force and determine where its line of action intersects the bottom edge of the bracket. So this is the bottom edge of the bracket, FE. So I'll select F as the reference point or the moment center for the calculations of moment in just a moment. Now, I have to present principle, although I presented this in the other videos, but I'm going to present it here. The principle for a pulley with tensions on either side and how to deal with them with it. So we have here, for instance, pulley, and we have tension 1 here and tension 2 here. The radius of this pulley is R. Just call it R. Now, by principle on one axiom of mechanics is that we can add two forces in equilibrium and at this center of the pulley as shown, T1 and T1. The effect of adding these two equilibrium forces is nothing because these two forces are in equilibrium. Remember that principle. And take note that this T1 going down and this T1 going up will constitute a counterclockwise couple, which is equal to T1 times the radius. So T1 times radius counterclockwise. Likewise, we can add another force system in equilibrium T2 at the center without changing the original effect of this pulley system as shown. So take note that the effect is the same as the original even without these two T2s that are in equilibrium, and by adding it, so the original system is unaffected, and this T2 here and this T2 here will constitute another couple which is clockwise. So we can remove these two tensions T2, we can remove these two tensions T1 and replace them respectively by their equivalent couple contribution. So that's why this system or the original system is equivalent to this system now. The forces T1 and T2 are now acting at the center after we remove the two T1s and the two T2s that constitute a couple as shown. Now, assuming that the counterclockwise couple produced by T1, so T1 times R is counterclockwise, is greater in magnitude than the couple produced by T2, which is clockwise. So the net couple is counterclockwise as shown here, and this is the difference between the couple produced by T1 and the couple produced by T2. That is T1R counterclockwise, then minus T2R clockwise. So that's why we have here the net uh, couple, and it can be applied anywhere by principle that the couple may be moved on any point on its or shifted at any point on its plane. So I'll just put it at the center. Then finally, if we have a condition where both sides of the pulley have the same or equal tensions, so T1 equals T2 equals T, for example, then this couple will just be zero because T1 equals T2, and there will be no couple here, just leaving T1 and T2, and take note T1 equals T2. So this original system can now be simplified further into this case here where we have two tensions at the center and there's no more couple because the condition is T1 equals T2. So that's the principle, and I hope that you can remember this because in statics there are many force systems, structures that are subjected to pulley systems, and that's the idea there on how to manage with them. So therefore, for this pulley here, we have two forces going down 120 and 160. By this principle here, I can replace it with a single force acting at the center going down equal to the sum of these two, and a couple which is clockwise because 160 is greater than 120, and 160 minus 120 is 40 times radius 2. So that's why we have 80 pound-ins clockwise. Or the other way, 160 times 2, 320 minus 120 times 2, 240. So 320 minus 240 is 80 pound-ins clockwise. In this case, we have force, add these two, 210 plus 150 is 360, same inclination 25 degrees, and it is now acting at B. Then the couple would be 210 minus 150 is 60 times the radius, which is 1.5, so 90 pound-ins, and it is also clockwise. So we now replace this system into the one that is in this system here. So we have 200 80 pounds, and we have a clockwise moment of 160 minus 120. That's 40 pounds, then times radius 2 inches. So that's why we have 80. And this is now the force representing this system here. It is equivalent to this. Now for this system, we have 360 pounds, 25 degrees up to the right, and the couple is 210 minus 150, 60 times radius 1.5. That's why we have a clockwise moment or couple of 90 pounds inch. So that system is now equal to this. So we can now compute Rx, which is just 360 cosine of 25, and Rx is equal to uh, 326.27 pounds. Likewise, Ry is 360 sine of 25 positive minus 280. So it is equal to negative 127.86 pounds, so meaning it's downward and Rx is rightward. We can now represent the resultant in vector form as quantity 326.27I minus 127.86J pounds. Now for the moment, as I said, I make F as the reference if you want E as your reference there, but I just choose F, and the components of the forces would be to the right and downward. It's at here. But before that, let's hold for the moment about using the original system and or the equivalent system. So obviously the moment is clockwise, and clockwise direction is negative. You can make it positive if you want, but in this case, let's stick to the sign convention that counterclockwise positive. So for the 360 pounds, we have two components, horizontal and vertical. The horizontal, the vertical component is counterclockwise, so let's treat that positive. Moment F is 360 sine 25 degrees times the distance is 12. So the vertical component produces counterclockwise moment about F, and it is 360 sine 25, and the moment arm is 6 plus 6, so 12. The horizontal component is 360 cosine of 25, and its distance from F, horizontal, it produces clockwise moment about F, and therefore it is minus 360 cosine 25 times moment arm 1 inch. Then for this one, for this 280 pound force, which is downward, it is clockwise about F. So minus 280 times 6, which is that. Then the two couples, clockwise couples, minus 80 minus 90. So moment about F is equal to negative 350.56 pound-inch, indicating that the moment about F is clockwise. Now, for the by Varignon's theorem for the components, so I put the components here at F. Let's say that's the position. The horizontal component of F passes through the horizontal component of the resultant passes through F. It has no moment. The vertical component, which is 127.86, is clockwise about F, so it's negative. So negative 127.86 times XF. I denoted the distance of the intersection of R with the bottom edge of the bracket as XF. So negative 127.86 times XF equals moment about F of the real system, negative 350.56. So from there, we can now solve XF, and XF is equal to 2.742 inches. So that's it for this problem. Problem 19. A couple M, which is counterclockwise in this figure, and the three forces, one, two, three forces shown are applied to an angle bracket. Find the moment of the couple M if the line of action of the resultant of the force system is to pass through letter A, point A, letter B point B, and letter C point C. So for part A, the analysis is if the resultant passes through A, then the moment of the resultant about A is zero. So that's the idea. Moment about A of the resultant is zero. And that is also the sum of the moments of its components about A, zero. So the idea in part A, moment about A is zero. So considering counterclockwise moment as positive, so we sum up moments about A and equate it to zero because MA is zero. So M, this has no moment because it acts at A. Then the horizontal component of 25 is passing through A, so it has no moment about A. The vertical component is 25 sine 60 degrees and it is counterclockwise, so plus 25 sine 60 times 12, and the moment of this 40-pound force about A is clockwise, so minus 40 times 8 equals 0. So that is M plus 25 sine of 60 times 12, then minus 40 times 8 equals 0. M plus 25 sine 60 degrees times 12 minus 40 times 8 equals 0. Solving for M equals 60.19 pound-inch counterclockwise. Then in part B, the resultant passes through B, so the moment of the resultant about B is 0. So the idea is moment about B is 0. So taking moment about B, 0. So M plus 10 times 12, then minus 40 times 8 equals 0. So MB is 0. M plus 10 times 12 minus 40 times 8 equals 0. Solving for M is 200 pound-inch counterclockwise. Then finally, if the resultant passes through C, so the moment about point C is 0. So our equation would be M plus 10 times 12. Then for this force, the vertical component passes through C, it has no moment, while the horizontal component 25 cosine 60 is clockwise about C, so minus 25 cosine 60 times 8 equals 0. So for part C, M plus 10 times 12 minus 25 cosine of 60 times 8 equals 0. Solving for M is negative 20 pound-inch. So because it is negative, it means M is 20 pound-inch clockwise. So that's it for this problem. Problem 20, a machine component is subjected to the forces and couples shown. The component is to be held in place by a single rivet that can resist a force but not a couple. So I hope you understand this statement here that the system can be replaced by a single rivet that can resist a force. So meaning to say, moment about that rivet is 0. It cannot resist a couple. So that's the idea. And it may be on this line FG. The rivet should be on this line FG or on this line GH. And the line of action should be extended, and we can move the components of that resultant along the line of action on line FG and on line GH. So I use G as the reference for the moment calculation in just a moment, in just a while. So let's solve for the x component of the force and the y component of the force. So Rx equals 200 cosine of 15 degrees, then plus P, which is 60, then minus x component of 120, 120 cosine of 70. So Rx is equal to 212.14 rightward. Ry, so all forces are downward, so I'll consider downward as positive. In a way, we will indicate it downward as the y component of the resultant force. So beginning with this, negative 250 sine 15, then negative, sorry, downward positive. So 200 sine of 15, then plus 120 sine of 70 downward, then plus 80 downward. So Ry is equal to 244.53 newtons downward. So the resultant, if we express it in vector form, is to quantity 212.14 I, then minus 244.53 J. Now, these are the two rivets, and the idea is moment about these 2 points would be zero because, as mentioned here, this system can be replaced by a rivet, single rivet, but not that cannot resist a couple. So these are the locations of the rivet. If the rivet is placed on this line FG, and if on line GH, this is the position of the rivet. So the components are placed, and we call this A. The rivet position at V from G is A. Then on line FG, the distance of that rivet from G is denoted by B. And these are the components of the resultants. So let's solve for the moment about G, and let's consider counterclockwise positive. Take note of the units. So 42 Newton meter, and these dimensions are in mm. So 42 and 40 combined because they are both counterclockwise. We multiply them by 1000 to convert them to, to Newton mm, because the moment of these forces would be Newton and mm. So moment about G is equal to quantity 42 plus 40 times 1000. Then let's begin with this force here. There are two components, horizontal and vertical. The vertical component is counterclockwise about G, so let's begin with that. 240 sine 15 degrees and moment arm is 50, so plus 200 sine of 15 degrees, moment arm is 50. Then the horizontal component is clockwise, so minus 200 cosine of 15. The moment arm is 520 minus 520 minus 50 because this is G. So 520 minus 50, that's 470. So minus 200 cosine 15 times 470. Then next we consider this force here. The horizontal component is counterclockwise, so plus 120 cosine 70. The moment arm again is 470, 520 minus 50. So plus 120 cosine of 70 degrees times 470. The vertical component is clockwise, so minus 120 sine of 70. The moment arm is 240 minus 50, that's 190. So minus 120 sine 70 times 190. Then for this P here, it's clockwise, so minus P, which is 60, and the moment arm is 130, not 180. 180 minus 50, this 50 here is 130. So minus 60 times 130. Then finally, 80 is clockwise, so minus 80 times the moment arm 640 minus 50, that's 590. So minus 80 times 590. So everything is accounted for. Compute mg is equal to negative 63344 Newton mm. So meaning to say the moment of the resultant about G is clockwise. So using the components by Varignon's theorem from the figure, moment of the resultant, which is downward here, the horizontal passes through G. So negative 244.53 times A because it's clockwise. and it is also equal to negative 212.14 times B, and the moment is equated to this value. So that is negative 244.53A equals negative 212.14B equals negative 63344. So we can now solve for A and B. A is equal to 259.0 mm and B is equal to 298.6 mm. Problem 21. Determine the reactions at the beam supports for the given loading. So let's draw the free body diagram. So the beam is in equilibrium. So that means static equations should be formulated. Namely, summation forces x must be 0, summation forces y must be 0, and summation of moments about any point is 0 also. So the free body diagram for the reactions at A, we expect uh, three reactions, horizontal, vertical, and resistance to moment, because this end is fixed as shown here. So these are the reactions. So definitely Rx, summation versus x 0. So Ax, the only horizontal force, is 0. So we have an answer. Ax is 0 as first. Next is you cannot you cannot solve for ay. We can solve for ay by summing a forces y, but we'll do that later. We solve for ma first. We sum up moments about a. So from the figure, counterclockwise positive, so ma counterclockwise plus 400 times this distance is 38. 6 plus 20, 26 plus 12, 38. Then equals or minus F1 times 2/3 of 12, 8 plus F2 times 10 plus 12, 22. So MA plus 400 times 38 equals F1 times 8 plus F2 times 22, where 22 is half of 2010 plus 12, 22. And 8 is 2/3 of 12, so 8. Remember the location of central triangle. So F1 is the area of this triangular line load, 1/2 of 12 times 50 pounds per inch. So that is equal to 300 pounds. F2 is equal to 20 times 50, and that is 1,000 pounds. So substitute into this equation, we can now solve for MA. So MA plus 400 times 38 equals 300 times 8 plus 1000 times 22. So MA is equal to positive 9,200 pound-inch because it is positive. This assumed sense, which is counterclockwise, is correct. Then summation versus y equals 0. AY plus 400 equals F1 plus F2. AY plus 400 equals 300 plus 1000. So AY is equal to 900 pounds upward. So that's it for this problem. Problem 22, determine letter A, the distributed load WO, which is this, at the end A of the beam ABC, for which the reaction at C is 0. So this is 0. The corresponding reaction at B. So at B, we have, because this is a pin, we have Bx and By. And at C, because this is a roller support, there's only one reaction, and that is vertical, perpendicular to the horizontal surface. And for this problem, this is a problem on equilibrium because uh, these are supports and the load is balanced by the reactions at the supports. So putting the reaction and the division of this loading, I divide this into two triangles as shown, and I'll call for this upper triangular line load F1, the equivalent force, and for this lower triangular live load, I call it F2. Then the reactions, we have 0 at C, By, and Bx as shown. So since there's no other horizontal load, We can therefore say that Bx is 0, summation forces x 0. So Bx plus nothing equals 0. So Bx is 0. Then to solve for uh, By, or to solve for Wo, by the way, F1 is located here, and the distance of F1 from the left is 1/3 of the base. So the base is 5 feet plus 7 feet, 12 feet. 1/3 of 12 is 4 feet. So this distance from the left or from A is 4 feet. But because this is 5 feet, it means F1 is 1 foot from B. Then F2 is 1/3 of 12 from C, from the right. So that is 4 feet also. And because this is 7 feet, the distance between supports, then this distance is 7 minus 4, so 3 feet. So applying now moment summation about B equals 0 because this is in equilibrium, the system is balanced. So counterclockwise moment F1 times 1, then minus clockwise moment F2 times 3 equals 0. The reaction at C has no contribution because it is 0 as stated here. So moment B is 0, so F1 times 1 minus F2 times 3 equals 0. What is F1? F1 is 1/2 of 12 feet by WO. So F1 is equal to 6 WO. F2 is 1/2 of 12 times 300. So F2 is equal to 1,800 pounds. Then substitute into this equation here, 6WO times 1 or 6WO minus F2 1,800 times 3 equals 0. So we can now solve WO equal to 900 pounds per foot. Then for By, it is just summation versus Y. So upward force By equals F1 plus F2. So By equals F1 plus F2. F1 is equal to 6WO, 6 times 900, while F2 is 1,800. So By is equal to 7,200 pounds upward. So that's it for this problem. Problem 23. The beam AB supports two concentrated loads. These are the concentrated loads and rests on soil that exerts a linearly distributed upward load as shown. So the soil reacts in a form of these line loadings or pressure. Determine the values of WA and WB corresponding to equilibrium. So again, this is a problem on equilibrium, that is summation versus y 0 and summation of moment about any point 0. So I'll divide this pressure intensity or trapezoidal line load diagram into two triangular line load diagrams as shown. So this is now the division, and I'll call this R1 for the area of this small upper triangle, and for this lower bigger triangle as R2. Now the location of R2 is 1/3 of 1.8 from the right, so zero point 0.6. The location of R1 is 1/3 of AB, 1/3 of 1.8, so zero point 0.6. So that means this 24 kilonewton load and this R1 are collinear in action. So it's better if we mark this as point C and we sum up moment about C to solve for R2 directly. So that is C, and our working equation is first moment about C is 0, counterclockwise positive. So we have R2 times this moment arm. Of course, this moment arm is zero point 0.6 because that's zero point 0.6. This is also zero point 0.6. So what remains is 1.8 minus zero point 0.6 minus zero point 0.6. So zero point 0.6. Then equals 30 times this distance, which is zero point 0.9. 1.8 minus zero point 0.6 minus zero point 0.3 is zero point 0.9. So R2 times zero point 0.6 minus 30 times zero point 0.9 equals 0. So from there, we can solve for R sub 2, and R sub 2 equals 45 kilonewtons. R sub 2, on the other hand, is the area of this triangle, which is 1/2 of 1.8 times WB. So 1/2 of 1.8 times WB equals R2, 45. So WB can now be computed. It is equal to 50 kilonewtons per meter. Then likewise, summation versus y equals 0. R1 plus R2 equals 24 plus 30. So R1 plus R2 equals 24 plus 30. R1 plus R2, which is 45, equals 54, or 24 plus 30. So 54 minus 45 equals 9. And R1 is area of this triangle, 1/2 of 1.8 times WA. So 1/2 of 1.8 times WA equals 9. So WA is equal to 10 kilonewtons per meter. Problem 24. So determine the reactions at the beam supports for the given loading. So this is the loading, and take note that the parabola extends and we have an upward pressure in this portion here. This is downward. So the reactions at A are anticipated as AX, AY, and moment, which is counterclockwise as shown in the figure. So again, this is a problem on equilibrium. So obviously, summation versus x equals 0. So AX is equal to 0. So that's the first answer. Then for AY, we need to solve for this loading. I'll call that F1. And this portion of the loading, which is upward, as F2 as shown. So I'll call the distance from B to the point where the loading is intersecting the beam or zero load as X1. And therefore, this distance is 5, 6 minus X1. Then we have, by squared property of parabola, 900 as to the square of horizontal, which is x1 square, equals 900 plus 300, which is 1200, as to the square of horizontal, which is 6 square. Remember that the equation of the parabola is in general y equals kx square. Y equals constant x square, where x is the horizontal. So y equals, or k equals y as to x squared. So y 800, 900, horizontal x1 square, then another y 900 plus 300, 1200 as to 6 square. So x1 is equal to 3 square root of 3 meters. Then we can compute this area by integration, but before that, let's locate, or let's name this as F1 and this one as F2, and the distance from here to any point as x, and we can establish this equation y by squared property of parabola, so that the strip will have a height of 900 minus y. So y as to x square again is equal to 1200 as to 6 square. Y as to x square equals 1200 as to 6 square. So the equation of this parabola, positive in this direction, is y equals 100 over 3x squared. Therefore, if we have a strip here, the height of that strip or loading would now be 900 minus y. And the thickness is dx, so we can evaluate f1 by integration as well as f2. Limits for f1 would be 0 to x1, which is 3 square root of 3. Then in the next slide, I will solve this problem in a better way or shorter way. I'll just have a loading condition to be added, and with sense the better way. So let's continue. F1 is the integral of this differential area, which is 900 minus y, the height, and the thickness is dx. Take note, this is the differential area of this strip. Height, which is 900 minus y, that's the height of that strip, and the thickness is dx, evaluated from 0 to x1, 0 to 3 square root of 3. And your calculator will have an easy way of evaluating that, even if we evaluate that manually. I will just evaluate this using the calculator. F1 equals 3,117.6 newtons downward. Now, F2, on the other hand, can also be evaluated, and it is the same because the curve is continuous, except that our limits would be from x1, which is 3 square root of 3, to 6, because that is 6. So f2 equals integrals 3 square root of 3 to 6 of 900 minus 100 x squared over 3 dx. So using your calculator, it will give us a negative value, meaning that it is upward. Negative 117.69. Summing up forces vertical, we can now compute AY. So AY plus F2, this is because that is upward. So AY plus 117.69 equals F1. So AY plus 117.69 equals F1. So AY is equal to 3,000 newtons upward. Then finally, for moment about A, I select B as the moment center. But before that, let's locate the centroid of this parabola from the right, from the load intensity, as well as the line of action of F2 from right. And we just use Varignon's theorem. Actually, I know that based on the derivation on distributed forces or centroids of areas, you can have that from integral calculus, but I already derived this, so I can memorize this. This is 3/8 of this parabola, 3/8 of x1. That's the expected value. And of course, for this case, it needs further analysis if we apply areas, but we'll just locate that by Varignon's theorem and using your calculator by integration for that part. So by integration, I'll call the location of f1 from the right as xg1 and f2 from the right as xg2 as shown. By Varignon's theorem, f1 times xg1 equals integral of moment of this differential force f1 is moment arm is x and differential area is of course same 900 minus 100 x squared over 3. So f1 times xg1 equals integral 0 to 3 square root of 3. Moment arm of the f1 is x, and this is the differential area, height 900 minus y dx. So using your calculator, the right side is equal to 6,075 Newton meter. So xg1 equals uh, 1.94856 meters. And take note, this is 3/8 of what I said of x1, this horizontal base. So 3/8 of 3 square root of 3, check it, it's 1.94856. So that for that parabola, you can just locate its centroid. This is the spandrel of parabola, and the centroid is 3/4 from the vertex for this spandrel of parabola, or the spandrel of parabola. And from the left end, it is 1/4 of 6 for that case. But don't mind because we're considering this parabola here. Likewise, negative 117.69 times xg2 equals integral of same x, then differential f, which is this. They only vary in the limits because for this f2 here, the limits would be 3 square root of 3 to 6. So solving for the right side using your calculator, it is equal to negative 6,675. So xg2 is positive 5.7354 meters. So there's sense because this is 6 and this is 5.7354 meters. Finally, we sum up moment about B considering counterclockwise positive. So MA plus F1 times XG1 then equals F2 times 5.7354 plus AY, which is 3,000 times 6. So that is MA plus F1 times 1.94856 equals F2, 117 clockwise moment, 17.69 times 5.7354 plus AY, 3,000 times 6. So MA is equal to 12,600 Newton meter counterclockwise. So that's it. I'll solve this again on the next slide. And let's have the shorter and easier way. So same problem 24, but this time I solve it in an easier way. But you have to understand and have this idea in your solution whenever you encounter this type of loading. So same questions, reactions at the beam supports, and this loading is now transformed into this loading here. The total load at the right is 1,200. Then there is a counter upward line load of 300 newtons per meter. Take note that at the right end, 1,200 minus, let's say, upward 300. So the net loading is 900, just like here. And in this part, this is 0. Then we have an upward loading of 300 Newton per meter. So that's why this loading system is equivalent to this loading system. But this is simpler in analysis than the one I presented in the preceding slide. But with your calculator and your skills in integration, that solution could also be a better solution, but it only needs your knowledge in integral calculus. But that is the same as this. And remember that I mentioned that the location of the centroid from the right is 3/8 of 6. So its location from the left is 5/8 of 6 because that is 3/8 of 6. So this should be 5/8 of 6. And the area of parabola, remember, is 2/3 base times height because the spandrel is 1/3 base times height. For this parabola, 2/3 base times height. Of course, this is a rectangle. The area is easy. I'll call the equivalent force for this loading as FD, F down. And for this force, equivalent loading is FU. And the location would be 5/8 of 6 because this is 3/8 of 6. And of course, this is 1/2 of 6 because this is just a rectangle. The reactions would be as shown, AX to the right, AY upward, and MA counterclockwise. So for AX, there's no other load, so AX is 0. That's our automatic answer. FD is 2/3 of base times height. So F down is 2/3 of 6 times 1,200, and that is equal to 4,800 newtons. While F upper is 6 times 300, and that is equal to 1,800 newtons. Then we sum up forces vertical, AY plus FU 1,800 equals FD 4,800. So AY plus 1,800 equals 4,800. So AY is 3,000 newtons, which is the same answer as in the preceding slide. Then for MA, I sum up moments about the right end. This time, we sum up moments about the left end A because the moment arms are predetermined and already labeled in the figure. So counterclockwise positive MA plus FU, which is 1,800 times 3, then equals FD 4,800 times 5/8 of 6. Solving for MA, it is equal to 12,600 Newton meter counterclockwise, just like in the preceding slide. Problem 25, determine the reactions at the beam supports for the given loading. So again, you use the idea in transforming this loading diagram to deal with this easily. So that is, you have a loading there and a loading in that manner. But I'll just leave it this way, and I'll solve this in this manner to improve your analysis. So let's just have these two triangular loadings. One is upward, the other is downward. So for the distance, I'll call that x1, and of course, this is 1.5 minus x1. Then to solve for x1 by similar triangles, imagine that this is a horizontal line. Then the total loading here is 900 plus 400, 1,300 Newton per meter. Then, then the distance is 1.5. So AX is 0. This is FD, that's F upper. And the reactions at A, we have 2 AX and AY. At B, there's only one because this is a ruler support. And this is again a problem in equilibrium because the loadings are supported by this beam. So naturally, this beam remains in equilibrium. So we apply static equations here. Summation forces horizontal, AX or RX should be 0. So AX is 0. That's one answer right away. Then to solve for the other reactions, we need to solve for X1, then the forces. So by similar triangles, X1 as to 400 equals 1.5 as to 1,300, where 1,300 is 900 plus 400. So x1 is equal to 6 over 13 meter. So that means the force Fu from the left is 1/3 of x1, and 1/3 of x1 is 1/3 of 6 over 13 is 2 over 13. Likewise, Fd from this load intensity is 1/3 of 1.5 minus x1. So summation moments about B equals 0. So FD is 1/2 of 1.5 minus x1 times 900, 1/2 of 1.5 minus x1 times 900. So FD is equal to 467.3 newtons. F upper is 1/2 of x1 times 400, and it is equal to, that's x1, 400. So Fu is equal to 92.31 newtons. Then we sum up moments about B equals 0. Clockwise this time is positive, counterclockwise negative. Anyway, that's the same. So meaning clockwise moments equals counterclockwise moments about B. So AY times 1.5 plus zero point 0.4, 1.9 plus 0.6, 2.5. So AY times 2.5 plus F upper 92.31 times its moment arm from B is zero point 0.6 plus 1.5, 2.1 minus 1/3 of x1. So that's why 2.1 minus 1/3 of x1, which is 1/3 of 6 over 13 is 2 over 13. This is 2 over 13. Then equals FD, which is 467.3, and its distance from the right is zero point 0.6 plus this is 1/3 of 1.5 minus x1. So moment arm 0.6 plus 1/3, that's 1/3 of 1.5 minus x1, 1.5 minus x1. So using your calculator, we can now solve for AY, and AY equals 105 newtons, and it is upward. Then to solve for RB, we sum up moments about A. So RB times 2.5, then plus FD, which is 92.31. The distance of FD from A is zero point 0.4 plus 1/3 of x1. So zero point 0.4 plus 1/3 of x1, 1/3 of 6 over 13, 2 over 13, then equals FD. This distance is equal to 1.9, 0.4 plus 1.5. 1.9 minus this distance here, which is 1/3 of 1.5 minus x1. So 1.9 minus 1/3 of 1.5 minus x1. So using your calculator, R sub B equals 270 newtons upward. So that's the answer, but let's check it. Summation versus y should be 0 because this is an equilibrium problem. So Ry equals Ay, which is 105, then plus Rb, which is 270, 105 plus Fu, 92.31, plus Rb, 270, upward, 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 then minus F downward, 467.3, then that is 0, almost 0. So okay, so that means these answers are correct.